Why is absolute zero, the coldest temperature possible, still beyond our reach? It's a mystery that's fascinated scientists and space enthusiasts alike for years. Imagine a place so cold that every atom, every molecule stops moving entirely. No motion, no heat, just complete stillness. That's what absolute zero represents. But despite all the advancements in science and technology, we've never quite managed to get there. Why is that? And why does this elusive temperature hold so much interest? Let's dive into the mystery together. First off, what is absolute zero, really? In the simplest terms, it's the point where all molecular motion ceases. On the Kelvin scale, which scientists use to measure such extreme temperatures. Absolute zero is 0K. That's minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. It's a level of cold that's hard to even imagine, colder than the coldest reaches of space. But here's the catch. No matter how close we get, we just can't seem to reach that exact point. The challenge begins with something known as the second law of thermodynamics. Don't worry, this isn't going to be a physics lecture. Basically, this law tells us that heat always flows from something warmer to something cooler. So, as we cool down an object, its molecules slow down and lose energy. But as you get closer and closer to absolute zero, it becomes tougher to get rid of that last tiny bit of heat. It's like trying to squeeze the last drop out of a sponge. It gets harder the more you try. But that's not the only hurdle. Enter Heisenberg's uncertainty principle, a key concept in quantum mechanics. This principle says you can't know both the exact position and momentum of a particle at the same time. As things get colder and particles move slower, this uncertainty becomes a big problem. The closer we try to get to absolute zero, the harder it becomes to control or even measure what's happening at the atomic level. It's like trying to grab a shadow. The closer you get, the more elusive it becomes. And then there's energy leakage. Imagine trying to insulate a house so well that absolutely no heat can get in or out. Sounds impossible, right? Well, that's pretty much what scientists are up against. Even with the most advanced cooling techniques, a little bit of energy always sneaks in from the surroundings. This tiny bit of heat keeps us from reaching absolute zero, no matter how hard we try. But things get even stranger at these ultra-low temperatures. That's when quantum effects start to kick in. Things like superconductivity and superfluidity. Superconductors can conduct electricity with zero resistance, and superfluids can flow without any friction. These are weird and wonderful states of matter that only happen when things are incredibly cold. But managing these quantum states is tricky. The more we try to control them, the more complicated everything becomes, adding yet another layer of difficulty to the quest for absolute zero. Let's not forget the sheer complexity of the equipment needed to get even close to absolute zero. We're talking about some seriously high-tech gear, dilution refrigerators, magnetic cooling devices, and more. These aren't your everyday appliances. They're intricate machines that require precise engineering and cost a small fortune to operate. So, while we've come astonishingly close to absolute zero, the process is anything but straightforward or cheap. Now you might be wondering, why bother? If absolute zero is impossible to reach, why do scientists keep trying? The answer is simple: curiosity and potential. By getting closer and closer to absolute zero, we're learning more about the fundamental laws of physics and unlocking new technologies. For instance, quantum computing, which could revolutionize everything from medicine to finance, relies on understanding how particles behave at these ultra-low temperatures. And let's not forget the practical advancements we've already made, like MRI machines, which use principles discovered through low-temperature research. The temperature we've reached is so close to absolute zero, it's almost beyond comprehension. thanks to some incredibly clever laser cooling techniques. But even that's not quite absolute zero. It's like running a marathon and collapsing just inches from the finish line. You're so close, but you still haven't quite made it. So, while we may never reach absolute zero, the pursuit itself is pushing the boundaries of what we know and what we can do. It's a quest that's more about the journey than the destination, and along the way, we're discovering new aspects of our universe that we never knew existed. Absolute zero might be unattainable, but the effort to reach it is driving some of the most exciting advancements in science and technology. And who knows? The next big breakthrough could come from our ongoing fascination with this ultimate cold. The journey continues, and with it, the endless possibilities of what we might discover next. Don't forget to hit that like button, smash subscribe for more jaw-dropping space updates, and join us as we embark on a cosmic journey like never before.